Ja, det startar alltså om 5 sekunder nu då, Åsa, där, så du är med och pratar då.
So, welcome to today's Swegon Air Academy webinar, Lowering Energy Consumption Without Compromising Comfort. And this webinar is broadcasted from the Swegon Air Academy platform, which is an objective knowledge sharing platform where we submit case studies, we provide this kind of knowledge webinars. We also publish articles and insights around the HVAC topic and indoor environmental quality topic. And we also publish books in this subject. So if you are interested in more info, you can visit our webpage and also follow us on LinkedIn. But back to today's webinar. Lowering energy consumption without compromising comfort. This is a really hot topic at the moment. And of course, it's due to the energy crisis and all the electrical bills that are rising at the moment. But it also has to do with the climate and all the building estates effect on the energy usage, of course. So the energy usage in buildings stands for almost 40% of the total energy consumption worldwide. And at the same time, we spend like 90% of our time indoors. So how should we compromise with this in a good way? And is the solution just to lower the temperature inside, or is there other strategies that might be more efficient? Because, of course, what will that has an impact on us as people if we just lower the temperature? What will happen with our productivity and so on? So let's dive into this subject with some help from expertise people that we have with us today. And our panelist of today and speakers is Åsa Wahlström, that is the sector manager for public authorities and trade associations at CIT Energy Management in Gothenburg. She's also an adjunct professor at Lund University and chairman of Sweden Green Building Council for certification. And also with us via link is Ida Bryn, who is the technical director for Multiconsult in Oslo, Norway. And she also have a doctorate degree in indoor climate from SINTEF. And here in the studio with me, I have Carl-Ola Danielsson, and you are R&D director for Swegon and the room unit products, which is the terminal units that we have in the room. And you are also a doctor in fluid dynamics. And beside you, you have Nicklas Svensson. Welcome.
Thank you.
And you have more than 30 years experience when it comes to ventilation, and your field of expertise is the air handling units. So let's dive into this topic, and Nicklas, you can start.
Yes. As you mentioned before, we are spending almost 90% of our time indoors. The same, this will give us a big, shall we call it, demand on good temperature and ventilation.
And good air.
And good air, yes.
Considering that we, during normal day, eat roughly 1 kilo of food, drink 2 kilos of liquid.
Yes.
But we breathe 15 kilos of air, 12,000 liters of air. 90% of that is consumed indoors.
Yeah.
The quality of the indoor air is important.
It's very important. At the same time, we should save energy. So what can we do? What can be done? If we start with the air handling unit, if you have an air handling unit that is set up in the correct way, you have a big, shall we call it, optimization already. And of course, you have also low energy consumption. So today we will talk about 5 important topics. We have the airflow, of course. We will talk about operating time. We will also talk about demand control, temperature, and maintenance. But we start with the airflow. As mentioned, the airflow is of great importance because if you have too low airflow, you will feel discomfort. You can lower the productivity, and also you can get health issues. On the other hand, if you have too high airflow, you can feel draft, and also you can have sound issues, and of course you will have unnecessary high energy consumption. You can see here on the right hand side 3 different airflows. This is an air handling unit with a heat exchanger. So you see the fan energy and also the post heating. So here you can see actually if you lower the airflow by 10%, you will also decrease the energy consumption with 20%. And so once again, make sure that you adjust the airflow to the facility that you have.
And Ida, do you have like input here when it comes to the airflow and also to balance that when it comes to infections, diseases, and so on?
Mike, of course, it's very efficient to reduce the airflow, but you have to be very aware of the corona or the infectious diseases. For example, Reva has made a guidance on this topic, and they show how the risk for becoming infected is reduced by increasing the airflow. So totally, it might be expensive to reduce it too low.
That's true. Good point.
Good. If we continue, maybe we should talk about the operation time. If you reduce the operation time, you will, of course, reduce the energy for the fans. Here you can see also 2 different diagrams where you can, for example, have changed the renter. So earlier on, you could have a renter, as you see on the left side here. You can have the operating time from Monday to Friday, 7 to 8 p.m. And with a new renter, you can reduce the operating time. As you see on the right hand side here, you will still have Monday to Friday, but you reduce the operating time 3 hours per day. So always make sure that you have the correct operating time in your air handling unit. And also don't forget during vacation and leaves that you also reduce or that you turn off the air handling unit.
Are there any risks by doing this?
Of course, depends on the type of facilities that you have. If you should turn off or if you should reduce the airflow, that depends on the type of activities that you have in the building.
So in order to try to quantify how much energy you can save by turning the air handling unit off, one thing you could do is to make simulations. And the result you get will depend on the building you have, on the location of the building, and the uses of the building. So it's very difficult to say that just turning the air handling unit off during night will save X amount of energy. But just to make an example, if we show here results from simulations that have been performed on a building, and the building is located in Gothenburg. It's an office building with high occupancy rate during office hours, and the standard of the building is very average according to Nordic conditions. So the average U value is roughly 0.5 watts per square meter in Kelvin. And we see then that we save roughly 40% of the energy required for heating by turning the air handling unit off. It's not a big surprise if we don't have a lot of cold air transported into the building during night. Of course, we will save on the heating side. I should say that this is also a system. That's another assumption made. This is a system where we have a constant airflow, and we're using a water-based system to add heating and cooling in the building. And no surprise either that we save on the fan energy. If we turn the fan off, of course, it will not consume any energy. So we save roughly 60% of the fan energy. If we compare to running it 24/7, if we run the fans between 7 in the morning and 6 in the afternoon. perhaps less intuitive is that the energy required for cooling is actually increased by 50%. So if you look into these numbers, you can see that part of the year it might be actually not a good idea to turn the fans off, because you will not benefit from the free cooling you can get from the outside air. Another way of adjusting the amount of air or the airflows is to have some more advanced control systems. And we're done talking about ventilation strategies. You can have constant air volumes, variable air volumes, or demand control ventilation. Considering that a person, depending on what you're aiming for when it comes to indoor air quality, one person would require between 5 and 20 liters per second. And some rooms and some buildings are not used 100% of the time. Taking a standard office building, there's a lot of conference rooms, perhaps designed for 10, 15 people that are used only a few hours a day. So then you can save significant amount of energy by using different control strategies.
And if you have like a new building or an old building, does that influence also this?
Partly. A new building, more tighter regulations when it comes to energy consumption. A new building is more often tighter. It is more well insulated, so it requires more energy for cooling. So, and then it's one way of cooling is to adjust the airflows. So many times, actually, the amount of air you put into your room is not to control the air quality, but actually to be able to control the temperature.
Ida, do you have any comments to this? And so what's about this CAV, VAV, and the DCV part?
Because one aspect is that, for example, if you have constant air volume, then it might be risky to try to have a low supply air temperature. Because then it becomes cold in some rooms. But when you have demand control or VAV, then you might use it as a cooling system. So you don't need an extra, at least in the Nordic countries. Or if you have control of the facade and the internal heat gains, you might be able to control the thermal comfort during hot periods only with a ventilation system. And then you reduced insulation costs, and you also reduced CO2 emissions related to materials. So that might be an advantage. But on the other hand, the challenge with at least the complex DCV systems is that they requires quite a lot more maintenance and following up, and might be complex for people that facilitate it. So I think we have a challenge to develop better digital interfaces to improve the possibilities for the facilitators to use the systems.
Yeah, we're talking a lot about when you also maybe change the occupancy with a new tenant in the building. I know we had some technical issues with you, but I don't know if you hear us and would like to comment now if you are with us. This with when we adjust, how often when we have a new tenant, what is the possibility to save energy there by recommissioning or adjusting to the correct flow? I think you are muted, Åsa, if you wanted to join us.
Is this better?
Yes.
It's a new system for me. This is something that we work constantly with the building owners, but it's something that you often don't have routines for, but you should actually change and do adjustment when you change tenants. And in luckily cases, you just use more energy than you need. But in the most, if it's not so lucky cases, you can have a new tenant but actually don't get the air that he needs. And so I think it's really important that we get in routines, that we always check how we need to adjust the system when we change the tenants.
And what do you think now when it's post Corona or COVID? A lot of people probably quit their maintenance contract and started up because they wanted to reduce cost and not to go bankruptcy with their business and so on. So how do you think they have come back and adjusted, and or is it a huge potential here with the maintenance?
I think it's still a huge potential, because even when we are back, we have a totally new pattern to work than we had before. And this is get great opportunities to actually save energy, but we also need to do it carefully so we don't make the indoor environment very worse for the ones that actually are at work. But I think we have to work with that much more, because the pattern haven't stable yet, I think. So during the next year, we will see a totally new pattern for that.
And Ida, in your market in Norway, you have a lot of air compared to like the other Scandinavian countries per square meter and person. And also outside of Scandinavia, you have the highest amount of airflow. So now when the energy debate is coming up, reducing like airflows and so on, how would you like to comment on that from a Norwegian perspective?
Yes, well, the regulations in Norway also has changed, so we don't have that high airflow anymore. It has become as a base became reduced, but it is more and more common to use the demand control ventilation system in almost all new buildings. They have it, and when we are starting renovating buildings, it now becomes more common to keep the old system but change it from a CAV to a DCV system. And so you keep the ducts and you change the appliances in the rooms and valves and so on. Sorry, I have COVID, so
sorry about that, Ida. But it's good that you are with us via link, then it's safe. Yeah. So Carl-Ola and Nicklas, did you have any comment more to what Åsa and Ida said? Or?
I think actually we can see it here when we talk about demand control. If we reduce the airflow, we also reduce, of course, the power consumption for the air handling unit and for the fans, of course. And we also know that if you have an air handling unit with the demand control system and you do small adjustments in the airflows, you will have quite big benefits on the power consumption in that case. So once again, if we reduce the airflow with 10%, we will reduce the power consumption with about 20%.
So then it's interesting to consider, we talked about operating times.
Yes.
So turning the air handling unit off was what we looked at earlier. We could say 40% of the energy for the fans, and we could say 60% of the energy for, 60% of the energy for the fans and 40% of the heating.
Yeah.
But instead of turning the fan off, if we have demand control possibilities, we could reduce it. And you said 10%, get 20% reduction in the energy. But nighttime, we could reduce it a lot more.
Yes, of course.
So we did some simulations just to test this. This is a slightly different, it's the same building, but instead of having a constant air volume system and the water-based system for heating and cooling, we're using a DCV system here, airborne system for cooling, but demand controlled, making it possible to reduce the airflows during nighttime. So instead of turning the fans off, we here reduce it to 0.35 liters per second per square meter. You could probably reduce it even further. We have assumed that the heat recovery of the air handling unit is not affected, and we know that actually reducing airflow might improve
it will improve the temperature efficiency. Yeah.
So then the result we get is that we consume roughly 10% more energy for the heating. And also here we have now considered that in this building we have district heating. If you have a heat pump, you don't pay the whole energy consumption there because you have a COP of the heat pump. So there's much less to gain of turning the air handling unit off. It actually might not be anything to gain. You have to look at each building.
Yeah.
And considering that the things in the building will emit things during the night. We have paints, we have carpets, we have furniture. And one common strategy is to turn the air handling off. And then 1 hour or 2 hours before people come to the building, you increase the airflows and to get rid of all the emissions. And considering this, it might be actually better idea in many cases to reduce the airflows.
Of course. And also if you can control the VOCs, as you said, you have the paintings and so on, which means that when the building is new, you will have a much higher airflow. But during the building getting older and older, the airflow will go down.
Mm-hmm.
Yeah.
Åsa or Ida, do you want to comment a little bit about this with the operating time for or shutting the air handling unit out during the night?
Yes, that's a very good idea, and you can air it out in the morning. But if the system, is it possible with the system to have a very low airflow during the night? I would prefer that and not shut it off completely. But it, of course, depends on the possibilities with the air handling unit, if it's going to do that.
Also looking at the energy prices we have, at least in the Nordics at the moment, more or less over whole Europe, that energy prices are much higher in the morning. Everybody wants to use electricity between 7 and 9 in the morning.
Yeah.
So.
And Ida, what are your comment to this?
If you really want to switch it totally off during the night, then it's very important to be sure that it is clean and dry, because if it's poorly with regard to that, you might get a risk of fungus, or what you call it in English, growing up. That might cause indoor air related diseases, and that is really not something we want. So, but that is always, it's important to change filters and to have a clean and dry system.
Yeah, so it could actually be a good idea to lower the airflow as much as possible, but not totally shut down the air handling unit, depending on what kind of system and building you have. And it shouldn't take too much more energy.
Considering now that the energy prices has skyrocketed during this last year, and we will see that it will continue for some time. We can see in the media lots of headlines how to save energy, or that there are plans of saving energy by adjusting the indoor temperature. It's in schools in Gothenburg here, where they plan to have 18 degrees inside. Same thing in Hungary. And during the summer, we could read in Spain that you weren't allowed to run your air conditioning system unless it was more than 27 degrees. Actually, I found this from BBC that the NHS in UK, they think about prescribing heating because people will save on the heating bills, and to help people who really need heating.
And I know, Åsa, that you are working with different projects to help and advise our government in Sweden, for example, with tactics or strategies to speed up energy efficiency in our buildings. But what is new when it comes to legislation here?
You mean the new? Well, we have a demand from Europe that we should reduce the energy consumption with 5% in public buildings, and of course this is very demanding to do, and must be done in the right way also. We talk about lowering the temperatures, but you must always check if the building, how the system looks in a specific building, if it's possible to do it without destroying the indoor climate for the people that work there. So it's a lot of thinking, and it's very difficult to give a general recommendation on how to do it, because you must really look into each building what is possible there. But it's really really tough to lower 5% for all buildings right now. So you have to think carefully what to do.
But it seems like the trend is that this the first thing you come to think of is to lower the temperature inside to a very low degree. So but how can you do it in the right way without taking too much energy out of the system?
Well, if we talk about modern systems where you have a heat exchanger, you have already there optimized the temperature efficiency actually, which means that you reduce the energy consumption for the post heating. So, for example, to give you some numbers, in the Nordic countries where we maybe have minus 20 degrees outside, we have a temperature efficiency of 82%. That will give you, after the heat exchanger, 14 degrees. So what I mean is that you lower the post heating in this case. You can also see here in the chart, there we have a heat exchanger with this air handling unit. You can see the fan energy, and by reducing the supplier in this case, by reducing the supplier with 2 Kelvin, you actually reduce the post heating with 90%. So it's good to know also that if you have a supplier some degrees under the room temperature, you will also get a good, shall we say, spread distribution of the air.
Ventilation efficiency.
In room level. So once again, a couple of degrees lower supplier temperature than room temperature will give you maybe better, should we say, indoor climate, because in modern buildings, you always, or big part of the year, you have a cooling demand, which means in this case, you have free cooling, so to speak.
Yeah, so instead of heating the supply air, providing heat to every room, even the rooms that have a cooling demand, we avoid heating and cooling at the same time in the building. So you could instead distribute the heat with the water system, for example.
Do you want to comment on that one, Ida?
This is something we very often discuss. And it might be a good solution if you have a demand control or variable air volume systems, because then the air is reduced if it's not needed, and you keep a steady temperature in the room. But in buildings with a CAV, it becomes too cold in the central areas and meeting rooms and so on if you reduce the supplier temperature, and therefore it's very common that you keep it on 20 degrees to avoid that problem. So that's another reason that demand control is a good solution. We also talked about reducing the temperature. What we have seen in Norway is that a lot of people they focus on setting down the temperature in areas that is not used, and that you decide you put people tighter in the tighter areas and set areas aside that you don't use, and that is also a strategy that can be used. There are other things also. It might be an increased risk for drought if you lower the supply temperatures. You have to have a system that works with that.
Good.
So Nicklas, you talked about the importance of energy recovery, and in the modern air units, we have very good energy recovery systems. So just to illustrate that, we did here some simulations. This is the same simulation on the right-hand side there from the previous one, where we had an airborne system, a TCV system. And we did another simulation where we turned the energy recovery system off. And we can see that the energy consumption for heating is increased a lot. Actually, using the heat recovery system with an 80% efficiency, we could save about 70% of the heat required. And I remember when I went to school, we opened the window to get some fresh air in. And then we let all the energy out. And we talk about heating. If we go further south in Europe, the same thing applies, but for the cooling side. You can recover the cooling.
Yeah, of course. If you have, for example, a rotary heat exchanger and you have a cooling demand, and the extractor is cooler than the outdoor air, you can actually have the cooling read in that case. Yeah.
And Åsa and Ida, what about the type of building? If you have like a smaller building, is there any potential to have another strategy?
Yes, what I think is in small buildings like dwellings or flats or even in buildings where you have one ventilation system for a small area, then it can be a strategy to really to skip the heating after the heat exchanger. Because then you might in Paris get a little low supplier temperature, but you will fully utilize the solar gains and the internal heat gains, and that might reduce the energy consumption quite remarkable.
And also, do you think what type of air handling unit you have is important?
Absolutely, it is. And especially, it's very important also how you distribute the air. If you are going to lower the temperature, you must really consider how it is distributed in the room. And so it's not just to lower it without thinking how it looks in the building.
Nicklas, you had some numbers you mentioned earlier. If you have an 80% efficiency of the heat recovery system.
Yeah, you increase the outer temperature from -20 to +40 degrees.
Without reheating.
Without reheating, yeah.
So in many cases that means that you can actually remove the coil needed for heating and save on the pressure drop.
It could be. Because at the same time you have some losses for the supply fan, which give you maybe a half degree or up to 1 degree, depending on the SFP value. So actually you could have 16, 17 degrees after the unit. And remember, now we talk about really cold outdoor climate, in this case, -20 degrees.
So we go further south in Europe, the need for the reheat coil is even interesting.
Yes, and the ambient temperature is increasing. We see that the minimum temperature in Oslo will increase from -20 to -16 or something in the next period.
Yeah.
But what we saw in the headlines earlier was that you actually talked about reducing or in the heating season, reducing the indoor temperature. So what effect does that have? So we did some simulation again, and in the previous ones, the set point for the temperature indoors during the heating season was 22 degrees when people are in the building during occupancy, and 20 degrees at unoccupancy. So we reduced that 2 degrees, 20 degrees indoor temperature, air temperature we're talking about, when people are in the building, and 18 when it's unoccupied during weekends and nights. And the result we get is that we save roughly 20%, or we decrease the need for district heating in this case by roughly 20%. And that is a little bit more than what you perhaps hear in the news when they talk about in Gothenburg, we would say like 5% per degree. But the reason for that is that we have a lot of internal heat gains in the simulations. So how much you save depends on the building, the location of the building, and the use of the building. But 20 degrees air temperature, is that good?
What about operative temperature, Ida or Åsa? Do you have any comments on that, and advice depending on what type of building and such?
If you have an old building with poorly insulated walls, you're more sensitive to low air temperatures, because the operative temperature is a mix of the surface temperatures and the air temperature. So I think it's easier to do this in a well-insulated building than in an old building or a building with big window areas and so on. So one should be careful or start to use sweaters.
or gloves. Åsa, do you have a comment on this one?
To also consider where the working places are situated. If it's close to window, for example, it can be not so good to lower the temperature. The operating temperature can be very tough in that case. You can usually count with 2 degrees less in operative temperature. So it's, yes. I think on the other hand, I think we can require also that we should have a sweater on in winter time.
Yeah.
So of course you cannot count on that you can go. You do not need any clothes at all. You can require to have a sweater, but of course you can't lower temperature more than that. And it also depends on, of course, of how long periods the people that work there have to sit down without moving around and get some kind of exercise in between. That can also be dependent on that. Yes.
So, for example, in a school, would that be more suitable or less suitable?
Often in schools, you at least have at least a break every 40 minutes, but you go out and go around and make your health system go around. So I think it's much more critical for people that sit and work 8 hours, and maybe they just take one break after 2.5 hours and so on, and sitting still quite a long time. And where, of course, they need because now we're talking going really low down in temperature, when it will become critical, definitely.
And the productivity will also go down if you.
Yeah.
Yeah. We have been touching upon maintenance and importance of that several times already, but this is probably one of the low-hanging fruits when it comes to saving energy without impacting the indoor climate. Actually, it probably have a good impact. Improve the indoor climate if we make sure that we have systems that are working as intended. So, looking at everything is installed as intended, you will be surprised how few systems are actually installed the correct way, that everything is commissioned as intended, and that you do the service according to some plan. And there are several different things that could go wrong. Filter changes, we'll come back to that. We see that poorly balanced ventilation systems or heating cooling systems, meaning that if you have a poorly balanced heating system, some rooms will be starved, so they don't get enough water or no heating. And the easy solution for that is to turn up the temperature. So because a few rooms might not get enough water because you haven't commissioned the water system, you increase the supply water temperature for the whole building. But then, depending on the system, if you have a heat pump, every degree you increase the supply water temperature costs energy because it reduces the COP of the system. Or you could have gas. It's not uncommon today that you have pipes that are made of plastic, and they're not. They can let in some gas, some air. And if you have air in the water that are supposed to carry the energy, it's a lot less efficient at carrying the energy, and then you lose a lot of the efficiency. And one thing that is extremely common is that we are heating and cooling at the same time. You have two different control systems and the set points are overlapping. And that is just a complete waste of adding heating and then adding cooling to remove the heat.
And also I thought about the Bryn system. If you have a system, you actually need to remove that and change that after maybe 8 to 10 years to have the same efficiency that you have when it's new. Also think good to know.
So how big of a issue is this? Is it a forgotten area, or how is the knowledge in this area? Is that something that it has a big potential when it comes to energy saving and comfort, or is it not?
I'm convinced that this is a huge area, and it's an area where it's tempting to save money by reducing the service, increasing the service intervals.
The problem is often that the service is actually to change filters. That is almost what you are doing in the service. Instead of going through the systems, check all the set points for the units, and also make sure that all the system is clean actually. Because if you have a dirt system or clogged up system, you will also increase the pressure drops for all the system. So
Also, is this something that you encounter when you are?
Yes. Yeah, I think the knowledge is quite good, but you know what you have to do with maintenance, but you often doesn't do it anyway, unfortunately, and not do it well enough. You do some things, but not regularly, and you don't have certain routines for the maintenance all the time. But I think that all building owners actually are aware that they have to do it, but still, they are not putting so much efforts on it, but it should be.
So it could be a hidden potential here, either or.
It has to be a change because now, as it is, you have routines. People come and check the systems, and very often this service is not very good. They just come and do the same things and leave again. They don't check the systems. But with the world we are living in now, where everything is possible to have digital, it should be really easy to use all the sensors you see there, and the sensor is in the system, collect them, analyze them, and give a message to the housekeeper, to the users, and to the people that maintain the system to tell them what to do. I mean, it's just it should be easy to make algorithms and do this now.
Yeah. And I think a lot of stuff is happening in this area, but I'm curious, like if you have a new building, then probably it's more opportunity to install a sensor, but if you have an old building?
But today with sensors that you can install and they can communicate wirelessly, it's actually not a big difference. It's quite easy to add sensors to an existing building and collect the data. And then you do it remotely, you have the system where you analyze the data. So this is, I think, a huge potential. It's a low-hanging fruit when it comes to use cases for the new technologies.
But I also think it's important then that we not only make this available for the people that maintain and run the building, but also for the people that own them, and that the housekeepers in the building, and those that have contact with the customers, and even the customers themselves should be able to see how the situation is with respect to indoor climate and the use of the energy in the building. That would make it more focused.
And I guess it also saves time, because you might find the problems in a more correct way, maybe address them. Or what is your experience from the systems you have?
Well, quite often when we get questions about things that are not working, just looking at the data that we collect, and we can quite easily from the office, without having to go to the building, we can find the problems and help out. And you can't imagine all the faults that you can detect. Things that, I mean, it's not that uncommon that the actuators are not connected to valves, or you connected the hot water to where the cold water should be. It happens all the time.
And also today you have in the air handling units, you have a lot of parameters that you actually can look at. You can actually get alarm if you have motor, for example, that consumes more energy than it should, and so on. So today we have really good systems. The problem is you need to know how to handle that.
Yeah, and one question that pops up is also sensors. Okay, it's fun to have a lot of sensors and technology and digitalization. Yeah, we all like that, but it's costly. So what should you focus on if you should put in sensors? Where should you put them, or what kind of sensors do you think is most relevant to help out with this energy efficiency and keeping the comfort?
Good question. I mean, there are some sensors that are not that expensive, like measuring temperature is a cheap sensor.
And air quality also, CO2 and so on.
Yeah, CO2 sensors are coming down in cost, but so they're more affordable now than they used to be. But we also see, looking at the simulations that we looked at, we saw that most of the energy is actually consumed for heating and cooling. So having control of the temperature, that you can save a lot of energy. But the CO2 sensors for measuring air quality is now very interesting, especially in this post-COVID times where the CO2 level is a good measure of the amount of people and compared to the ventilation. So there are other benefits than just energy savings, making sure that the whole system is operating as intended.
How do you see this, Åsa?
I can comment. Also, it's of course very good with a lot of sensors that you put in all building, but often you just put in the sensors and you must educate the operation staff to handle the sensors. How should they read them and how should they handle it? And that often fails, but the operation staff have not the knowledge on how to use this new information. And I also see very much that you just go out in the building and make the quick fix of problems that you have in the indoor environment, and that becomes always in a way at using unnecessary much energy. And you do this quick fix all the time without reporting that this is a problem here, that we do really need to make a larger adjustment. So I think we also need not just to put in sensors and think that everything will be solved. We really need to educate the operation staff to use the new system if it should save energy in the end as well.
Good. But one focus I know is like the filter exchange, Nicklas.
It's maybe the easiest way to actually make sure that you save energy. Make sure that you change the filters in time. As you see on this on the screen here, you can actually see that initially, you can see that the pressure drop over filter is quite low actually. But when it starts to increase, it increases quite rapidly. So make sure that you change the filters in time. Of course, if you have clogged filters, clogged heat exchangers, and so you will also increase the pressure drop, which means that you will need more energy for the fans. And as I mentioned before, for the heat exchanger, if you plug that one, it will increase the pressure drop, but it will also reduce the temperature efficiency.
We see here in the graph that initially the pressure drop is, say, 75, 80 pascals, and then after 14 months or so, we have doubled it. Yeah. But what does that mean in terms of energy?
You can actually follow the curves for the pressure drop in this case. So you will have the increase of energy. We follow the curve of the pressure drop in this
so it's a one-to-one relationship, more or less?
Yeah, okay. More or less.
Interesting. Okay, we have now talked about a lot of different actions you can take to save energy. But where do we start? What should be the strategy when it comes to saving energy?
At the bottom.
Because we're dealing with a lot of different markets and geographical areas, and so how should you think if you're a property owner or facility manager and so on?
And we think that this Kyoto pyramid has been developed to give some advice, and it's I think applicable more or less everywhere. You should start from the beginning, from the bottom, with the base of the pyramid, and then look at how can you reduce the heat losses? How can you reduce the need for cooling? And in the simulations that we looked at earlier, the building that we used had fairly good, I would say, compared to the average building in Europe. The U values were good, the windows were good. So that would be one thing to start with, to make sure that you have a good building envelope. Because the reasoning is that the building will stand there for 100 plus years, whereas all the systems might be replaced within 20, 25 years.
And we have talked about the heat recovery and cooling recovery. Quite easy to make sure that you have those factors.
Yeah, big impact.
Yeah.
good return of the investment.
Absolutely.
And we talked about changing the set point for temperature, and it goes both for heating and cooling. So
Yeah.
allow higher temperature if you have a high need for cooling, and lower temperature if you have a high need for heating.
Yeah.
So moving upwards in the pyramid, we're talking about reducing electricity consumption. We talk about pressure drops.
Yeah.
We talked about operating times.
Yeah.
So turning the unit off, of course, saves energy.
And here we also know that the demand for the SAP is increasing. We know in Sweden, for example, we have today demand, or should we say recommendation, that we have SAP value for 1.5 when you have a heating coil. If you have a heating coil and cooling coil, the demand or recommendation is 1.6 kilowatts per cube and seconds there.
And keep moving up. We should try to utilize as much of natural energy as possible, so not having to add energy. We saw the effect of the free cooling.
Yeah.
When we looked at turning the air handling unit off and we had a constant air volume, we saw that the demand for cooling actually increased.
Yeah.
Because we didn't get full use of the free cooling during the nighttime. And, sun, if you can let the sun in during the heating season, during the winter time, but keep it out during the cooling season, you could save quite a lot of energy. And we see now a huge interest in Europe to replace gas boilers and use ground source heat pumps or air source heat pumps, both for heating and cooling.
Yeah.
And then moving up, you should look at visualizing and using controls. So visualizing data that you collect from the building in order to find areas of improvement where you need to work with the maintenance or faulty installations or commissioning. And then clever controls, demand control.
Ida, Åsa, do you want to add something to this?
I think it's a bit forgotten. It's when you have a heat recovery systems, you have freezing protection because the exhaust air might be humid, and if it's freezing temperatures outside, it might the exchanger, the humidity might freeze in the refrigerator, in the heat exchanger. And so it's a lot of different systems to avoid this. And what we've seen that it's very little consciousness around it, and very often it's too simple way to control it. So often they just set if the exhaust the temperature becomes lower than, for example, 0, then you reduce the heat exchange efficiency. So, and I think it's a big potential to focus on this and to choose the better systems that we know exist, because of the high ventilation rates, at least in Norway, the indoor humidity is quite low. So, and then you can have a lower exhaust temperature as well.
Åsa?
Yeah, I totally agree that it's important to make sure that we don't have frost protection from the air handling unit. But I would like to comment on that you took out the Kyoto pyramid or the energy pyramids. But this is, I really like this design strategy, and I think it's explained very well how you should think when you make a well optimized building. Of course, when you go up, as you explained, for each step, it always will be in loop. Again, you have to compromise with certain things and so on. But it's a very good strategy to think on. And I wanted to give some credits, but you can also use this every time you, for example, change a tenant in the office. You can go back to this Kyoto pyramid and look at it again. Are the supply units placed at the right place? Do we have Do we have the right times? Can we make some more demand control of the ventilation and so on, and go through this pyramid once more every time? So I'm very glad that you point this strategy out. I think it's very good.
So that is what you want to give to the viewers of this webinar. If you should sum up like 2 or 3 stuff, that is go with the Kyoto pyramid every now and then when you change the tenants, or
yeah, not completely strict, but to have the main thinking in these steps, and then of course you have to make some adjustments in it. You can't take it really strict, but have this thinking. You will come a long way in reducing energy without compromise with the indoor climate.
Ola, do you want to comment?
No, I just want to say that if you don't follow this and you start in the wrong end, say you start with replacing the heating system with a new heat pump,
Yeah.
then you need to buy a much bigger heat pump than you need if you instead start with insulating the building, reducing the need for heating. So that's also a reason why you should start from the base to get the right size of all the equipment you need.
Yeah. Otherwise, it will be hard to accomplish a good comfort, I guess, as well.
Yeah, if you have a system that is not sized for the task, it's much harder to control it. So yeah.
And Ida, do you, if you should send something with the viewers here, to points?
Yes, I fully agree. This Kyoto pyramid is very, very pedagogic and very useful, and we use it all the time when we're planning as a strategy to design buildings. It might vary from case to case, but they're the same principle. That you start with reducing the demand, and in the top you select the energy source. So, and if you do it opposite, you might end up very wrong, because you might have a too big heat pump and with a low efficiency and so on. So.
Great. So I think that we are at the end of the presentation here. So now we are opening the chat for comments or questions to the panel, of course. But we have a short of time, but if you write questions, we will come back and put that on the web page as well in Q&A. We have a comment from Richard Sang about the enthalpy wheel can work without freezing at -40 degrees, depending on the relative humidity of the indoor air. It's a big topic in the Canadian market.
Yeah, it is. And actually, we are looking at that right now. But we know that the freezing is beyond the aluminium wheel. So, but we will come back to that later on and see the exact moment when we get freezing in the social wheel.
Good. Is it anything that you want to summarize, Carl-Ola, to give some points with the viewers here? What you think is the most important, except the Kyoto pyramid?
I would say the Kyoto pyramid. No, I think to stress once again that we showed some results from simulations, and the simulations they are, and you need to consider each building as an individual. The different location, different type of windows, different usage of the building. So what actions to take you need to be considered from building to building.
And of course, in 1 hour, we are not allowed to dig deep, but we love to. So if you also have a request about a topic in the future, please send that in to us at Swegon Academy, of course. And if you are interested in more topics and the presentation afterwards, you can also go in and find that on your link, and we will also send out a follow-up email from this webinar. If you want to watch other webinars that we have sent throughout the year about IEQ topics, LCA, EPPD, you can surf into swegonacademy.com. So here you have all the 6 knowledge webinars that we have sent previously. And in mid-January, we will publish the calendar for next year's webinar series. So follow us. And I would like to say a big thank you to Åsa and Ida for joining us today, and also Nicklas and Carl-Ola here in the studio. It's a really interesting topic, and I'm sure that we can come back and dig deeper into this in the future.
Yeah.
Yeah.
So thank you for listening.